Dear all, welcome back to Computer Organization and Architecture class. And today we are going to see the continuation from the Unit 1. In Unit 1, we have discussed the first topic is about the introduction to computer organization and architecture. And today's class, we are going to discuss about number systems. So followed by the introduction of organization and architecture, we are going to discuss about number system. In number system, if you see the any integer numbers can be returned positional with respect to positional number systems. So general format of any number system can be represented mathematically by using this formula. That is n is equal to a n minus 1 r power n minus 1, where n is the number of digits. Now, how many number of digits we have got? For example, 97,142, we have got 5 digits. So where n is the 5 digits for this particular number. So in this formula, where n is the number of digits and R is the radix. So R is the radix. The radix can be varied from 0, that is AI. That is, the radix can be varied from 0 to R. The value of a radix can be varied from 0 to R, which is represented by using AI. Okay, so where R is the radix number system, that is by base. You can also call this radix as a base. The base can be what? A binary or a decimal or a octa or a hexa. So all these are referred as a radix or bases. So any number system can be represented with respect to what? From n minus 1. That is r power n minus 1 and also its coefficient should be multiplied with this coefficient. The coefficient denotion will be a n minus 1. A n minus 1 into r power n minus 1 and also a n minus 2 r power n minus 2 plus it is a naught, then a1 r power 1, a2 r power 2. So with respect to positive and negatives, they'll be represented by using this structure. Now, here, as we have already discussed about, R is your radix and N is the number of digits. So, for example, if you take the number 97,142, how it could be represented as per this formula is 9, the first digit. Okay, the first digit, this is actually the a n minus 1. So 9 into how many digits we have got? This will hold a position of a power 0. This will hold a position of 1, and this will hold a position of this is r power 0, r power 1, r power 2, r power 3, r power 4. The weightages can be given for these things are r power 0, r power 0. Suppose if it is represented by using a radix called a decimal, then r will be what? 10. R will be 10. So the weightage for the first LSB. LSB starts from here and it ends with the MSB 9. So this LSB holds a value of what? 10 power 0. The weightage here for 1, 2, 3, 4. It goes on like this. So this value is, this representation will be R power 0. Here R is a decimal. So it is 10 power 0, 10 power 1, 10 power 2, 10 power 3, 10 power 4. They are actually called as r power n minus 1, r power n minus 2, r power 2, r power 1, r power 0. And the coefficients will be the number itself. So 9, 7, 1, 4, 2, they are all actually the coefficients. They are represented by using a n minus 1, a n minus 2, a2, a1, a naught. Did you understand? So this is how any number system could be represented. So if you take a binary, binary means again the radix will be what? 2. But the position, the weightage for all number system would start from 0 to n. So n minus 1 actually, because we are starting from 0, so it should be taking the value of n minus 1. So if it is a binary, the radix will be 2, so it will be 2 per 0, 2 per 1, 2 per 2, 2 per 3, 2 per 4. If it is an octal, the radix will be 8. So that is what the same thing will be here given here. If it is a decimal, the radix will be 10 and the coefficients are what? From the range 0 to 9. Because we know that we have got an unique decimal values only from 0 to 9. Binary means what are the unique values? We have got zeros and ones. So binary means the base or radix. The radix is also known as a base. So the base or radix for binary will be what? 2. And what are the distinct values or different values that binary holds is 0 and 1. Similarly, if you take a octal, the radix or base for octal is what? R is equal to 8. And the coefficients will ranges from 0 to 7. So octal values always will ranges from 0 to 7. If you take a hexadecimal value, it will take a value of a base of our radix value as 16. So its coefficients, that is coefficients we are representing as per our number system as A. So this coefficients will vary from the 16 values of hexadecimal digits of coefficients are from 0 to F. So 0 to till the decimal value 9. And from for 11, 12, 13, 14, 15, 15, we are having the values, that is letters. By using alphabets, we are representing equivalent value for 10, 11, 12, 13, 14, and 15. So for a equivalent decimal 10, the hexadecimal value representation in terms of alphabet is A, and for 11 it is B, and for 12 it is C, for 13 it is equivalent hexadecimal value is D, for E it is 14, and for F it is 15. So these are the different number systems we have got. For example, they have explained here in detail, like digit positions. For example, if you take a decimal number system, one by one, we are going to discuss in detail about the number systems. First, if you take a decimal number system, decimal number system means what we have said, the radix will be 10. So the digits, the coefficients of the 10 values are actually from 0 to 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are all could be the coefficients for decimal. And decimal will take both integer position and fraction. See, a number can be represented with respect to its decimal part as well as that is integer part as well as its fractional part. Okay. Floating point number can be represented by using a decimal number system. So it has got two portions, integer as well as fraction. The fraction will be differentiated by using a dot. And the weightage, how the weightage will be given base per position. We have seen, right? R per 0, R per 1, R per 2, R per 3. Likewise, how it will be given a weightage base to the power position. So position for this integer starts from LSB 0 to MSB 1, 2, 3, etc. up to n minus 1. Similarly, the position for this in fraction part will be starting from -1. Next to the dot, the position for this fractional part will be given as -1. So -1, and what is the base for decimal system? It is a 10. So the weight for this is 10 power -1, and weight for this is 10 power -2, 10 power -3. It goes on like that till 10 power -n. So magnitude will be what? Digit into weight. The coefficients are what? Exactly the numbers, and also it should be multiplied by using its weightage. So weightage will be calculated by using base into the position. So the weightage for will be for 10 power 0 it is what? 1. 10 power 1 it is what? 10. So 10 power 2 it is what? 100. So these are all the positional weights for the corresponding integer portion of the decimal system. The position for this what? 10 power -1 is 0.1. 10 power -2 is 0.01. So with this, the magnitude values like 4, 7, 2, 1, 5 are multiplied respectively. So that the final representation of this particular number in decimal system will be what? 512.74. It is a base 10. Decimal means we have to represent by using a base what? 10. Decimal means we should represent a base of 10. So the 512.74 with the number system expansion, it will be taking a position of, it can be expanded with respect to 2 into 10 power 0. 1 into 10 power 1, 5 into 10 power 2, and 7 into 10 power minus 1, 4 into 10 power minus 2. This is how decimal number system would be represented. Next, we'll discuss about binary number system. So binary number system is also the same procedure it follows. Only difference is what? Base will be true. Base will be true. So base will be true. And here also we have got both integer portions as well as fractional portions. So, and again, it will be represented by using magnitude into weight. Okay, binary number system also will be represented by using magnitude into weight. What is the magnitude? These are all the values, all the binary numbers, zeros and ones are nothing but your magnitudes. And weight will be what? Again, the weight formula is base per position. So positions are what? R per 0, R per 1, R per 2. What is your base here? What is your R here? What is the radix for your binary? It is a 2. So for as per the binary system, this position, this weightage is what? 2 per 0. This weightage is 2 per 1 and this weightage is 2 per 2. And similarly for this decimal part or fractional part, what is the weightage? 2 per minus 1. It's same like a decimal. Only the thing is they should be 2 instead of 10. That's it. So it's a 10 2 per minus 1 and this is 2 per minus 2. So with respect to this base per position, you should multiply its magnitudes. So magnitude of this particular binary is what? 1. So 1 into 2 power 0 and 0 into this takes a value of 0 into 2 power 1 and for 1 it is 1 into 2 power 2 plus and what is its fractional parts? It is minus 1 into 2 power minus 1. This is 0, right? Its magnitude is 0. 0. So 0 into 2 power minus 1 and plus this value, this magnitude is what? 1. 1 into its position is what? 2 power minus 2. So 1 into 2 power minus 2. With all these computations, if you just do, it will have a value of 5.25 in terms of decimal. So equivalent to decimal representation is 5.25 and its corresponding binary representation is 101.01. And also if you see in binary number system, 4 bits can be referred as a nibble. Okay, nibble. 4 bits. 4 bits together is called as a nibble and 1 byte is nothing but 8 bits. 8 bits are together called as a byte. For a representation of the bits, the group of number of bits can be represented with respect to different names. So 4 bits together is called as a nibble and 8 bits together it is called as a byte. Next, similarly, octal number system. Octal number system means what we have studied, what we have seen. It bases 8 and it will take a digit values. It will take the values from what are those 8 values, coefficients or the number. For octa, it will take the coefficients or magnitude for octa, it will take the values from 0 to 7. So 0 to 7 is the octa number system. So it will take a base of value of 8. The total value of octa number system is represented by using 8 and the 8 values are 0 to 7. So if you see here, the same decimal system, 512, how it can be represented by using an octal means, this position is actually again what? 0, this is 1, this is 2, and this position is minus 1 and minus 2. So these weights are represented by using with respect to its base. The base for octal number system is what? 8. So its position is what? 8 power 0. Its position is what? 8 power 1. Its position is what? 8 power 2. Similarly, this position is what? 8 power minus 1. This position is what? 8 power minus 2. So everything is added together and multiply these weights. These weights with respect to the coefficients are 2. 2 into 8 power 0, 1 into 8 power 1, 5 into 8 power 2. Similarly, in the fractional part, it is 7 into 8 power minus 1. 4 into 8 power minus 2 will give you the equivalent decimal number system, decimal value. So decimal value, it's equivalent to decimal value. So since it's a decimal value, it's represented by using what? A decimal, that is 10. Next, if you see about hexadecimal number system. So hexadecimal number system is what? Same procedure, but its base is 16. So the hexadecimal number will have a base of 16, and the 16 values are from what? 0 to all, like decimal, all 0 to 9s. And after 9, for the remaining 5 or 6 bits, the remaining 6 bits, they're represented by using the alphabet called A to F. So for 10, it is A, letter A, 11 represented by using B. For C, it is a 12. For D, it is 13. For E, it is 14. For F, it is 15. So the base for hexadecimal number system is 16. So again, the position for what, how this position will be represented? 16 power 0. This position is 16 power 1. This position is 16 power 2. Any other octa number we have got here means they'll be represented by 16 power 3. Similarly, this position after the decimal point, after this decimal point, after this fractional point, and next to the point, whatever the value, that is whatever the number you have got here, it will take a weight of what? Yeah, as per your hexadecimal number system, it is 16 power minus 1. This is takes a value of 16 power minus 2. So if you just multiply its coefficient with respect to all its weights, so 5 into 16 power 0. E means what is its equivalent value? It is a 14. So 14 into 16 power 1. And 1 is 1 into its position is what? Its weight is what? 16 power 2. Plus, similarly, the coefficient for this fractional part is 7. And its weightage is 16 power minus 1. This position weightage is 16 power minus 2. And its coefficient A. A is equivalent decimal is 10. So if you write all this expansion and simplify this, add it, add it and simplify this, you will get the value of this. This is an equivalent decimal number for a hexadecimal of this particular value. So this is one simple procedure to convert any number-based conversions. Decimal 10, a decimal system between decimal octal. This can be the relationship, the short memory you can have in order to have a conversion between different number systems from decimal, octal, binary, and hexa. So if you have a decimal to octa, you can able to convert decimal to octa indirectly, but octa to decimal directly you can able to convert. So the dotted lines represents an indirect. Similarly, binary to decimal, you can evaluate its magnitude. And hexadecimal, if you see the direction, hexadecimal to decimal, direct conversion is possible. Decimal to hexadecimal, you have to convert by using indirectly. Similarly, binary to hexadecimal also can be done through decimal number systems. So different relationships between conversion of octal, decimal, binary, and hexadecimal has been given here. So next we will see about the conversions. That is from one base, one radix to another radix, so how the number would be converted. If at all you have your number only in certain base, or if you want to convert that into another base, how we will do that? So different conversions between, we have seen that the number systems is of what? Decimal, binary, octa, and hexa. So between these number systems, how the conversions could be made, we'll discuss about it. The first conversion would be decimal to binary conversion. How we can convert a decimal to binary conversion. For integer, we'll discuss first, then we'll go for a fractional part. So if at all we have a decimal integer numbers, okay, the integer numbers, the decimal value in the integers we have, okay. So divide this integer by 2. Okay, first divide this integer by 2 and take the remainder as either you will be having a remainder as 0 or 1 that should be considered as a coefficient, and take the quotient and repeat the division. That is the procedure you have to follow. For example, you have got here 13, right? So you have got a 13 here. So first what we have to do, 13 should be divided by, as per the procedure, this is the rules we have to apply for a conversion. We have to take a decimal number and divide that by 2, and we'll have a 0 or 1 as a reminder. That should be considered as a quotient, and whatever the that should be considered as a coefficient. Whatever the quotient we have got, with we have to continue the step 1 again until we are getting the remainder as 0 or 1 as your quotient. So what will happen is 13. You take a number, given number is 13. First divide the number by 2. So what is that divided by 2? We'll have a quotient as 6 and remainder as 1. So coefficient, the first coefficient we have got is 1. And then what is the quotient? This is the quotient. This is not 0 or 1, right? So this is more than 0 or 1. So again, we have to divide that by 2. Okay, so divide that by 2 so that what we will get? The remainder will be 0, quotient will be 3. This will be the next coefficient 0, noted down. Again, take the quotient again, continue the step. Continue the, whether you are getting your quotient as 0 or 1, until then you just continue the step 1. So again, 3 should be divided by 2. So you'll be having what? The quotient will be 1 and the remainder will be 1. So note down its quotient, note down its coefficient. That is, remainder should be the coefficient. Note down its coefficient as 1. Again, you've got what? Quotient as 1. So you've got a quotient as 1. This quotient can be divided by 2, or along with this quotient, you can complete your conversion. So you've got your quotient as what? Quotient as 1 here. So it's not a larger than 2. You have got either 0 or 1 itself. So here itself you can stop the division, and from here itself you can just take your conversion for binary. So what are the conversions you have got here? 1 and then 1, and this coefficient only represented here as 1, and the next coefficient is a1 and this will be a0. So with respect to all this in reverse order, so whatever the last coefficient you have got, that should be the first one should be represented in binary. So from here 1, next a2, a1, a0, you represent them. These coefficients, they are the actual binary equivalent of the number decimal. This is how a decimal should be converted to a binary. Divide them by 2 continuously until your quotient becomes 0 or 1. Okay. And for each and every time a division, you take a reminder, note down the reminder in the order. Okay. They should be written in a reverse order finally in order to get the binary equivalent. This is how the conversion of integer of a decimal to be converted to binary. So if you see here, no, other examples, 25 divided by 2, 12 divided by 2, so 25 divided by 2. So 25, if you want to convert 25, no, 25 is the decimal. For the equivalent binary, how to convert 25 divided by 2, okay? So you will get a 6. Remainder will be what? 1, right? So you will get your quotient as 12. Again, 12 should be divided by 2. So 12 divided by 2 will give you the remainder as 0, and it will give you what? The quotient as 6. For example, I'll just work out this 25. Okay, 25 to convert into binary. Divide this 25 by 2. So you will get what? 12, right? 12 will be the quotient and the remainder will be 1. Again, this should be divided by 2. So what you will get? 6. But remainder will be what? 0. Again, divide this by 2. So what you will get as a quotient 3. Remainder is 0. Again, this should be divided by 2. So what will be the quotient? 1. What will be the remainder? Again, 1. So this equivalent binary, how to represent binary in the reverse direction? Okay. So in the reverse direction, what are the reminders you have got? 1, 1, 0, 0, 1. So this will be the binary equivalent of a number, decimal number 25. Okay, this is how you have to do the conversion. Okay. So next we are going to discuss about what? Decimal fraction to binary conversion. So for converting decimal fraction to binary conversion, what you have to do is multiply the number by base 2. Multiply the number by the base. The base for binary is what? 2. So multiply the number, the first fraction number by 2. Okay. Take the integer. Okay. Take the integer as a coefficient. Whatever the integer you get in the result of the multiplication, whether you will get either 0 or 1, that should be taken as a coefficient. Take the resultant fraction and repeat the division. Again, repeat the procedure, that is the steps 1 and 2. We'll see with an example how to convert. For example, this is the fractional part of your decimal, 0.625. So 0.625, in order to convert into a binary, what we have to do is, what is the first step? We have to multiply it by its base 2. So take 0.625, multiply it by 2. Okay. So what you will get, multiplication, the resultant of 0.625 into 2 is 1.25. Okay. Take only the coefficient. Okay. Take only the coefficient and take only this coefficient and note it down. This will be referred as a minus 1. Okay, for fractional part, we have to write the fractions in binary format in the same order as they are obtained. Okay, so this should be a minus 1, whereas in integer part we'll write in reverse order, right? But here we have to write it in the same order which we are obtaining. How we are obtaining a power minus 1. Again, what is the fractional part we have got in the previous result? 0.25. This should be again multiplied by 2. So what is the result you will be getting? 0.25 into 2 will be 0.5. Okay, so this 0.5 means 0.5. The 0 will be considered as a coefficient and this 5 will be considered for next multiplication by 2. So 0.5. So 0 will be the coefficient, that is next coefficient a minus 2. Again 5 should be, this 0.5 should be multiplied by 2. We'll get 1.0. Until we are obtaining 0 as the fraction, you can do this. If at all you are not at all getting a fraction of 0, you can continue for 4 or 5 steps, then you can stop it there. So 0.5 into 2 will be 1.0. So its coefficient will be 1. It will be referred as a minus 3 and the fraction is 0. So you can stop here the multiplication by 2. So for 0.625, the conversion, the equivalent to binary value is, you have to represent the coefficient in the same order 101. So it is the representation for this 0.625 in binary is 0.101. Since it's a binary, you have to represent by base 2. This is the converting decimal fraction into a binary. Same example is given here. And these are all the different equivalent numbers for the important decimal numbers for 1 to 10. How the binary can be represented? Binary values 1, 1, 0, 1, 1. You see, they are already converted so that if you remember this, it may be useful for saving the time. And next conversion is decimal to octa conversion. So how to convert decimal to octa? Before that, we have seen decimal to binary. Now it is decimal to octal. So decimal to octa follow the same procedure. Instead of binary, binary means we have to use a base 2. Okay. Octa means the same procedure like decimal to binary. Instead of base 2, you have to use a base 8. So for converting the integer part, you have to divide the decimal number by 8 until you are getting the quotient which is less than your 8. Okay. So you will be having 8 or until getting 0 you do it. So take the least number also in while you are writing your binary or octal conversion. So yeah, 175 by 2, 8. You will have a remainder as a 7. So that will be considered as a coefficient A naught and quotient again to be divided by 8 because it's not less than 8. So again, how to divide by 8 and you'll be having 2 quotient, which is actually less than 8. Here also you can stop it here. So 2 will be actually A2. Okay, this is the coefficient A2. This will be the coefficient remainder A1. This is the coefficient A naught. So the equivalent 175 decimal, the equivalent octa value was 257. This is how you have to do it. as we have divided by 2, right, in the binary, here we have to divide by 8. The same procedure, divide by 8. That's it. The same procedure you have to follow. Similarly, here for a fractional part, the same procedure as we have said, right? So what we should do, what is the procedure? This should be multiplied by 8, and the fractional part will be considered for coefficient, and that is that integer part will be considered for coefficient. Fraction part should be used for the next procedure to be followed. Again, the same procedure, that is using the previous fraction, we have to multiply by them 8 until we are getting the fraction as 0. So in the second step itself, we have got fraction as 0. So here itself we can stop, and this should be written in reverse order. And but here if this should be written in the same order. So by equivalent to 0.3125, the equivalent octa fractional conversion is 0.24. Did you understand this? Similarly, next, decimal to octa conversion, decimal to hexadecimal conversion. So decimal to hexadecimal conversion is what you yourself can able to do. How to convert any decimal number will be represented. Any decimal number will be, that is the integer part should be treated differently, and the fractional part should be treated differently. And how the integer part we have to do, instead of the base 2, here we have got what is the base for hexadecimal? 16. So entire decimal should be divided by 16 until you are getting a quotient less than 16. And each time, whenever we get the reminders for the division, those reminders should be saved here in the order. And finally, we have to write all the coefficients, that is all the reminders in the reverse order. That is how we have to convert your decimal into hexadecimal value. So 1983 divided by 16, you will get 120, remainder as 15. Again, 123 should be divided. So you will get a remainder as 11. Again, 11 should be divided by 16. So you will get your quotient as a 0 and remainder as a 7. So in the order of a remainder, we have to reverse order of the remainder. We should write the answer for decimal to hexadecimal conversion. This is the equivalent hexadecimal value. Okay, 7. And for 11, equivalent hexadecimal is what? B. For equivalent 15, the hexadecimal value is what? F. So for 1983, the hexadecimal conversion is 7BF. Same way we have to do for fractional part. Fractional part should be multiplied by what? 16. So you will be having its integers. You will get the integers and a fractional part. So fractional part should be multiplied again by 16. Every time the fractional part should be multiplied again by 16, generate the integers. They are actually going to give the coefficients. But here, if you consider in the first time itself, the fractional part is 0. Whenever getting fractional part as 0, you can stop the multiplication there itself. We can stop the conversion there itself. So here, fractional part we have got already 0. So you can stop the conversions. So only with respect to one step, that is a one integer value, that is 9. With this coefficient, we can stop the conversions. So with this coefficient 9, the equivalent fractional part will be represented by 0.9. This is how the conversion from decimal fractional part to hexadecimal conversions, hexadecimal fractional parts. Next is binary to octa conversion. This can be done by using one short procedure, short step. How the binary to octal conversion? If you consider octa conversion, no, octal means what? It is 8. Okay, so 8 can be represented in terms of 2 power is 2 power 3. Okay, so we're using 3 bits. Using 3 bits. This 3 can be equivalent for number of bits, conversion to number of bits. So with the 3 bits, any octa value can be represented. That is, any binary value in terms of octa can be represented. Okay. So if you consider the octa 0, okay, in binary, how it will be represented by using a 3 bits. Okay, by using 3 bits, it can be represented 0, 0, 0. Okay, so any octa value can be represented using a binary with respect to 3 bits. So this holds the value of what? 2 power 0. Okay, this LSB take the weight of 2 power 0. This next LSB take the value of weight of 2 power 1. This as weight of 2 power 2. So if we just expand 2 power 0, 0 into 2 power 0, 0 into 2 power 1, 0 into 2 power 2, the value is equivalent to 0. That's its equivalent octa. Similarly, if you take 1, 1 can be represented by using what? 0, 0, 1. Okay, 2 power 0 will be 1. So it's equivalent to 1. Similarly, 0, 1, 0 is B units for. So this position is as per octa. This position is what? 2 power 2. It's a 4. Its weightage is 4, 2, 1. Okay. So octa will follow the code weightage of 421 code format. 421 code format. Any octa value from 0 to 7 can be represented in binary using 4 to 1 code. Okay, so 0 can be represented by using all zeros. 1 can be represented by using 001. 2 can be represented by using 010. 3 can be represented by using 011. 4 can be represented by using 100. 5 will be 101. 6 will be 110. 7 will be 111. This is how it can be done. For the decimal point also, that is the fractional part also, you can follow the same procedure. Okay, this is how to convert a binary to octa conversion. And similarly, binary to hexadecimal conversion. So if you take the hexadecimal conversion, octa means it is 8, right? So hexa means it is 16. So 16 in terms of 2 power is 2 power 4. So for every hexadecimal value, the binary can be represented, equivalent binary can be represented with respect to 4 bits. Okay, so 4 bits means they'll be taking the weightage of 2 power 0, 2 power 1, then what? 2 power 2, then 2 power 3. Okay. So if you just expand them, it follows the code of what? 8, 4, 2, 1. So this hexadecimal will follow the 8421 weight code. Okay. So any number, any hexa number 0 in terms of binary with the 4 bits can be represented by using 000. 1 will be represented 0001. 2 will be represented 0010. Similarly, all the values from 0 to F can be represented by using binary by using this 8421 code, which follows like this. So F will be represented what? All one ones. Because 8 plus 4 plus 2 plus 1 will be 15. So all positions, if we give 1, 1, 1, it will become 15. It's equivalent to F value. Then if you see after to hexadecimal conversion, after to the hexadecimal conversion, directly you cannot able to do either by using binary in between or decimal in between. You can convert the octa to decimal. So octa to decimal we already discussed. So octa to decimal you convert and then convert to hexa, or octa to binary you convert then convert back to hexadecimal. If you see here, this is an octa number. So convert this into binary first. How to convert octa into decimal, that is octa into binary. With respect to 3 bits, we have to represent. So for 6 can be represented by using 4 to 1 code as 110. 2 will be represented as 010. Similarly, this 2 will be represented 010. And now you just group them into 4 bits because we want what? At the end, we want the value as hexadecimal. So we have to group them into 4 bits. So for fractional part, assume 0 at the end. Okay. And for this integer part, assume zeros, extra zeros at the left side. Okay. Group them into 4, 4. If you are not able to group them, shortage of 4 bits means add 0, 0 at the left side. Okay. For fractional part, add zeros for extra zeros at the right side. So group them into 4 bits and convert equivalent decimal value. Those 4 into 8421 code. By using 8421 code, convert them into equivalent hexadecimal value. So this will become 16.4 will be the equivalent hexadecimal value for the octa value 26.2. For the basic number 0 to F, what are the octa value, hexa value they were represented. So thank you all. So this is what about today's class. We have discussed about number system and the corresponding conversions from different the decimal number system to different number systems like a binary, octal, hexadecimal. And also we have seen the conversion from octa to binary and hexa to binary. Also we have discussed about conversion from uh, octa to hexa by using a binary. Thank you all.